Well, let me start with the Galerkin formulation of a 1D diffusion problem. And I will be introducing some concepts step by step. So let me make some simplifications at the beginning and then extend it. Good. Diffusion problem. Let's assume we have started with the Laplace equation. So in 1D, basically something like that. Or we might have, or maybe let's start with the Poisson equation. So we've got some source term on the right-hand side. We've got the steady state equation. If we transform the strong form to the weak form, then what we would end up with is, I think we have also derived that for 1D recently. So just check me. I think what we would arrive at is du dx times dv dx integrated over the omega equals, we need to integrate the source term, and what we would have is we would have this for 1D. We have said it's nothing else than taking the difference of the between the values on the right end of the interval and at the left boundary of the integral of the interval. So correct me. I think this would be nothing else than du dx times v calculated at x. Well, let me introduce some domain 0 with proper finite element discretization. We've got n elements. So at x equals 0, x equals L. Right? Good. So is it already a discretized equation? No, it isn't. So it's just the weak form. It's just the weak formulation, but still the continuous, in the infinite dimensional function space. So we have no way solving something like that on the computer. We need to translate it to a finite dimensional function space. So basically do the discretization for, well, as many functions as we want to represent. Typically in finite elements, if you introduce the space discretization by dividing into subdomains, what we are doing at the same time, I mentioned recently, let's imagine taking one element, zooming it in, and in such an element, we've got two local shape functions or test functions. One of them would be like that. The other one would be like that. Let me make one comment at the end. I don't want to put it now. Test functions, global, local. Okay, so we want to exploit these shape functions at the same time test functions to discretize that equation. Okay, so how many nodes do we have? I equals 1, 2, 3, 4, 5, 6. So let's assume we've got n elements. And elements n plus 1 nodes. Okay, then, see, what we need to do, having n plus 1 nodes, having 6 nodes, means we have 6 unknown scalar values that we need to solve for. True? We've got one scalar value in each node, so we've got 6 unknowns, which means that if we want to solve such a linear equation, then we need to have 6 algebraic equations that we generate somehow by using this weak form to have like a well-determined system of linear algebraic equations, right? Good. So what renders the equations are the test functions. As we've said recently, like the sense of the weak formulation is that we are taking as many different test functions as we wish, and we use it to test whether locally somewhere the equality between the left-hand side of the equation and the right-hand side of the equation, if it holds. So taking arbitrary many test functions, taking each particular specific test function will render one discretized equation. So to come up with the equations for each scalar value at a certain node, what we are doing is we are using each of these test functions, and the test function, okay, I will touch this comment. The test function, let me redraw that a bit bigger. 1, 2, 3, 4, 5, 6. It's L, it's 0. How does a test function for the third node looks like? It looks the following. If we already exploit the linear one-defined element, this means that, well, the test function at node 3 has got value of 1 and 0 at all the other nodes, which means it looks like that. And it needs to be integrated over the whole domain. So the test functions, if we are speaking strictly mathematically, the test functions are global. They are defined everywhere in the domain, not just within one element. And taking such a test function for, let's say, third node will render one equation, one algebraic equation. So, well, basically what we are doing is we are saying we've got the I, and our I needs to, I equals 1 to n plus 1. Okay, fair enough, but we are not done. It's not really having full discretization because we need to remind how we represent U. And U at x, we represent it by taking the that's good. By taking the sum over all nodes, uj will be the scalar value at the jth node times the Jth shape function. Okay? So far, so good. Or maybe let me use phi. It will look a bit better than capital N all the time. Good. So what we need to do is we need to, and obviously the test functions are exactly the same. We are, and we need to start thinking about that in the global sense. So as said, the test function is 1 at a certain node, so it gives non-zero value at both adjacent find elements. Okay, so it's definitely one part of that particular global shape function or test function, and the other one. The same applies for the shape functions. These functions to represent the field. Very, very often, if you think about finite elements, you mainly are thinking about local shape functions inside one element. But for the sake of formulation, mathematically speaking, they are global functions. So let's do the discretization. And there's not much to be done.
Why don't we use some non-linear function? For example,
we will.
Like that. We can.
If you define that a single line element has only 2 points, then you can use only linear functions because you can only span linear functions on 2 points.
Yeah.
But if you have 3 points, you can have parabolas.
You cannot, for example, define finite elements like something like that. No, you can't. Basically, because it would introduce some arbitrarity. Because as Mateusz said, well, maybe you can do it like that. Maybe wider, maybe more narrow. So you can't determine such a shape based on just two values. You need to assume something additionally. But that's one side of it. The theoretical problem is that I think I cannot show the proof immediately, although it's not difficult. But one of the requirements for the shape functions is that shape functions, it said, they should be partition of unity. They need to be a partition of unity, which means that adding all the shape functions together needs to sum up to a global field of 1 everywhere. And no, the function. If you take such a function and the other function and you add it, you sum it up, then everywhere here will be 1. If you take the next one, everywhere here will be 1, and so on and so on. And all the global shape functions must be partition of unity. And I think it's not difficult to show. Simply, you would not. Well, even I think it's mainly because if you want to discretize something like that, just a source term, which is everywhere 1, and your shape functions do not fulfill that, you would end up with wrong results. And I think it's pretty easy to show that you must fulfill this requirement of partition of unity. And if you take something like that, you might end up with a field which is like something like that. So if they do not fulfill the partition of unity, they will be wrong.
Just like if we assume that our solution is constant, and if like we had because we have that formula for the U, which is sum of U j Vj. So if we got like constant solution and the same values in all nodes, and if the phi wouldn't fulfill that condition, like we would have not constant solution.
That's true as well.
And what about second order meshes?
There is no problem with that, because if you define the second order finite elements, you've got, well, one shape function would look like that, the other would be like that, the third one would be like that. If you sum them up, they really sum up to unity.
Okay, so I wanted to check if we are still using this linear the second order, or we have something else.
No, with second order, it's fine. Even if you go to the 10th order and you define spectral element method, they still fulfill this requirement. Good. So what we need, we already know that our VI will be nothing else like simply phi I at x. What will we need? We will need the derivative with respect to x. So dvi dx equals nothing else as taking phi I at x with respect to x. That's pretty obvious. Let's differentiate that. du with respect to dx is nothing else as taking the, well, differentiation is linear, summation is linear, so that's nothing else as sum j components do not change. The only thing we need to differentiate are the shape functions with respect to x. And let's write the final discretized form just by substituting this and that under our integrals. Good, so we've got integral omega sum over j uj d phi j dx. Let me skip the argument. Well, times d phi I, here is j I dx, and let me write the integration element d omega equals, well, what do you do with the source term? Basically, you assume, like in every finite element, that within the area of the element, it's interpolated by the same functions. So you can write explicitly f at x equals, again, sum j f j times phi j at x. So you've got well-defined shape of the source term field. Okay. Omega. Fj, phi j times phi I d omega. And, well, let me omit that for a minute. let me just say that we will need this term if we want to implement the Neumann boundary conditions. If we do not want to implement Neumann boundary conditions, but the Dirichlet conditions, we will need to change something, but we can assume we are interested in Dirichlet for now, and that one will not be needed. In a couple of minutes, you will understand why. But if so, then we are already fine with our discretized form. But just, it may not be very, very clear, so let's make a couple of comments about that. First of all, we've said that looping over the index I, and so looping over the test functions associated with each particular node in the mesh, renders the subsequent equations in our algebraic system of equations. So taking I equals 1 and looping to 6 will render 6 algebraic linear equations. Then, so changing I will render the next equation. Now, unknown values. Clearly, we are interested in solving for the U function. So our unknown values are the Uj values, U1, U6, and that's fine. And right now, just let's see what we need to calculate. Let's imagine that we want to write the find element discretized equation for the value at the third node. So what we are doing is we're saying, okay, let's select I equals 3. So I is already set. What do we have here? We've got everything that is left is just the sum over j, and let me rewrite it slightly in a way that I will take the summation out of the integration. Integral phi j dx phi I dx times Uj equals, well, actually here it doesn't matter so much. What we do, let's do the same thing. Vj phi I times Fj, if you will, here d omega. Fj, if you wish. And let's comment again. We've set I, we're rendering the equation for the third node. What's left is here, just one index because we've set the other one. And this will be the integral of the gradient of the shape function of the test function times the gradient of the shape function, where these functions are well defined within the domain and like they do not change with the solution. So it's something that you can calculate. Once you've chosen what your shape functions or test functions will be, you can simply calculate this value. Uj is the unknown. So that will create the two indices. So this will create a matrix. Selecting I and looping over j will render the subsequent values of the matrix for the third unknown. Is it clear?
Yes, it's clear.
Good. So this one, this matrix, or the ijth element, is the diffusion matrix. And see, what we can also do is we can if you have a look at just that, you see the source term is probably explicitly known. You know its values. So what you could do, you know that, well, in the original integral, that was nothing else as just the f function. And you could integrate it multiplied by some test function. And you can do it right away. Or you can derive such a formula with two indices, so again, a matrix, and multiply it by the nodal values of f. And such a matrix is called, exactly, is the mass matrix. Okay, so far so good. So let's really assemble the 1D discretized equations. All right, first of all, the only thing that we will need are the derivatives of the shape and test functions. So let's see. If we take if we consider this find element, what would be d phi 2 with respect to x? So you see this shape function which has got nodal value of 1 here and dropping to 0 here. What is it? Over? Yeah, and what's the d? Dx is probably L divided by number of elements, right? Okay, so far so good. D phi 3 with respect to x, then 1 divided by delta x, right? So now, let me go step by step by explaining two things. We've come up with this formulation, and as you see, this formulation is fully global. We already know that phi functions are defined everywhere. We also know that we need to integrate over the whole domain. It's not something particularly convenient. Also, taking into consideration that you want to define a find element method which should be computationally effective and efficient. But you can observe that obviously such a test function, if we define them this way, then the test function itself, even if you multiply by the test function, not the gradient of the test function, then you see, okay, it's non-zero only in the elements adjacent to a particular node and is guaranteed to be 0 everywhere else. So clearly, you can replace this integral over the whole domain simply, even in the 2D case or 3D case, having a huge mesh means that you only need to integrate in the adjacent fine elements and you don't need to integrate anywhere else. Well, if you've got the gradient, same thing, like it's non-zero here and 0 everywhere else. So we already know that, to be honest, we do not need to integrate over the whole domain, just over the adjacent elements. And then we come up with a procedure that it's much easier to assemble finite element equations, not when thinking about global shape functions and global test functions, but thinking about local shape functions and local test functions. So then we start looking at this element, and in a minute we will need to look at this element to complete the integration of the third test function, because integrating in this element means actually only taking the half of the contribution, but then we need to move to that equation and also integrate the third test function over the area of the adjacent element to really fulfill this equation. So it's much easier to define local matrices for each element and then assemble the algebraic system of equation. So let's write the diffusion matrix, local diffusion matrix for, let me call it first element, second element, third, fourth, fifth element. Let me write it like that. This will be the diffusion matrix for the second element. Well, and let's use this formula to compute it. What is it? Luckily, all the terms are constant. So what do we need to do? First, we define the local element. The local element has got the second node and third node. Okay, so to say we will have indices, 2, 3, global indices, 2, 3, and we need to calculate all the terms. What do we need to have here? Well, like J2, I2, so it's -1 divided by delta x times -1 divided by delta x, right? Times, we need to integrate all of the area of just one element then, because we will be integrating over the other element as well. And what's the area of the element? It's delta x. Good? Then, second gradient of the second function, it's again -1 divided by delta x times this one is plus delta x. Integration means let's multiply by delta x. Then just let me focus right now. Let me exploit one of the properties of the matrix, properties of the diffusion matrix. We've been calculating phi2 times phi3. If we move here, we need to calculate phi3 times phi2, and we see it's the product, so we can flip the order, and we'll still have the same result. So it's -1 divided by delta x times 1 divided by delta x times delta x. And here we need to multiply that 1 divided by delta x times, again, derivative of the third test function times delta x. Let's simplify. Well, minus, then we can do it like that. It's 1 divided by delta x. It's minus 1 divided by delta x. Here again, minus 1 divided by delta x. 1 divided by delta x. Okay? Clearly symmetric matrix, and it's the formulation of just one local diffusion matrix.